Welcome to the Radical Renewal Spa, where we allow every root to discover its true power. Here we change your aesthetic, but never your value. Let's begin. Here you are, a simple radical, the square root of x. Since there is no number but the radical symbol, the index is automatically 2. The variable x is the radicand, and I will be calling radicands the subject throughout the video. Keep in mind, for the video, there will be no negative subjects. The domain of all subjects presented will always be greater than or equal to 0. To convert a radical to an exponent, take the subject and put it in brackets. Then, outside the brackets, you're going to give the subject a fractional exponent. The numerator is always given a number 1, and as for the denominator, it will get a number that is the index. In this case, the number will be 2, since that is the radical index. Now, using the exponents, multiply the fraction outside the brackets by the exponent of the subject. Since x has no visible exponent, it's automatically to the power of 1. Therefore, the square root of x is equal to x to the power of 1 times 1 over 2, which equals x to the power of 1 over 2. After multiplying the exponents, the brackets can be removed. And that's all. That's the procedure. Nothing complicated nor crazy. As the index changes or increases, so does the value of the denominator to match it. In other words, the index and the denominator are always the same value. Since we're dealing with radicals here, the index is always greater than or equal to 2. It's pretty much safe to conclude that all radicals written as their fractional exponent become 1 over the index. For more detail on the structure and definition of a radical, a link will be posted below. Also, if you need to refresh your understanding when it comes to the laws of exponents, that information will also be posted below. Now, what happens when the subject has an exponent other than 1? A quick note, we are going to ignore 0 as the exponent since anything to the power of 0 is 1. Let's take a look at the square root of x to the power of 2. Just like previously, to convert it to a fractional exponent, put the x to the power of 2 in some brackets. Then, outside the brackets, give it an exponent with the numerator being 1 and the denominator being 2. Now, multiply the exponents to get x to the power of 2 times 1 over 2. That's equal to x to the power of 2 over 2, which is equal to x to the power of 1, or x. All right, let's say we have the square root of x to the power of 3. What does that look like? Put the x to the power of 3 subject in brackets and place the exponent 1 over 2 on the outside. Now multiply the exponents to get x to the power of 3 times 1 over 2. That gives us an answer of x to the power of 3 over 2. Let's look at this expression, the fourth root of a to the power of 5. Place the subject a to the power of 5 in brackets and place a fractional exponent on the outside. The numerator is automatically 1 and the denominator is 4 since the index is 4. Multiply the exponents to get an answer of a to the power of 5 over 4. See, very simple. If you notice, the final value of the numerator depends on the original exponent of the subject. The exponent of the subject ends up becoming the numerator of the fractional exponent after multiplying. Okay, now check this out. Here we have the radical as the denominator. What happens here? How do we convert that to an exponent? The same method we used for the square root of x is the same method we use even when it's a denominator. Put subject x in brackets, put the fractional exponent 1 over 2 outside the bracket, and now multiply the exponents to get x to the power of 1 times 1 over 2. Therefore, 1 over x to the power of 1 over 2 is the final answer. Guess what you also have the option to do? You can flip the numerator and denominator to get x to the power of negative 1 over 2. When it comes to exponents, they can be converted into a negative or positive if the numerator and denominator are switched. For more detail on understanding negative exponents, a link will be posted below. Now, beware of a common mistake. Let's look at 1 over the square root of x again. When we place the subject x into brackets and give it the exponent 1 over 2, this is what we get. Flipping the numerator and denominator changes the exponent from positive to negative or vice versa. This might cause the mistake of making exponent 1 and exponent 1 over 2 both negative. The best way to think about it is like this. The fractional exponent given by the radical always stays positive. Once the exponents have been multiplied, then the final answer can have a negative exponent. My advice would be to multiply first, then flip if necessary. Are you with me so far? If this is how you feel right now, that's perfectly fine. Just relax and practice with the basics. Let's revisit the rest of our previous radicals, but this time we'll turn them into denominators. Once converted to exponents, this is what we get. Just remember one key fact. All these forms are just fine. One isn't quote-unquote better than the other if used as a final answer. Flipping into a positive or negative exponent isn't a must, but you should know how to do it just in case. Depending on the expression you're asked to work with, one form might be more appealing to use than the other. Take this expression, for example. The square root of x times the cube root of x squared. If both radicals had the same index, we could simply combine them under one radical. But in this case, you cannot just multiply the subjects under one radical when both indexes are different. So the step that must be taken is to convert both using fractional exponents. When separate radical expressions are being multiplied, divided, added, or subtracted, it's important, if needed, to focus on each expression individually. Convert to fractional exponents individually as pieces, then bring them together. For the square root of x, its fractional exponent form is x to the power of 1 over 2. For the cube root of x squared, its fractional exponent is x to the power of 2 over 3. Now, we can bring these forms together and rewrite the expression like this. Since both share the same base, which is x, we can use the law of exponents and add the exponents together. That means that x is to the power of 1 over 2 plus 2 over 3. That gives us an answer of x to the power of 7 over 6. Okay, let's have a look at this expression. Here we are dividing with the radical numerator, while the denominator isn't a radical. We can remove the radical by writing the square root of a to the power of 3 like this. Now, since we are dividing values of the same base, we can subtract the exponents. That means that a to the power of 3 over 2 divided by a squared can be written as a to the power of 3 over 2 minus 2. That gives us a final answer of a to the power of negative 1 over 2. This can also be written as 1 over a to the power of 1 over 2. With this expression here, we first want to focus on what's happening in the brackets. The subject has a radical index of 5 and is to the power of 3. Therefore, we can write it out like this: z to the power of 3 over 5, all to the power of 2. Now, all we do is multiply the exponents, and that gives us a final answer of z to the power of 6 over 5. Let's have fun with this expression. Here we have 1 over the square root of x to the power of 3 times x to the power of 1 over 4. To simplify, we'll convert the square root of x to the power of 3 into a fractional exponent. When converted in the denominator, this is what we get. X to the power of 1 over 4 over x to the power of 3 over 2 is a correct answer, but we can simplify it further. Since we are using the same base x, that means it can be written as x to the power of 1 over 4 minus 3 over 2. After subtracting the fractions, that gives us a final answer of x to the power of negative 5 over 4, which can also be written as 1 over x to the power of 5 over 4. Here we have a cube root of b to the power of negative 1 divided by the square root of b to the power of 3. Again, since both radicals have a different index, we'll convert them to their fractional exponents. Starting with the cube root of b to the power of minus 1, after multiplying the exponents, we get b to the power of minus 1 over 3. For the square root of b to the power of 3, that gives us b to the power of 3 over 2. Now that we're done converting, that gives us b to the power of negative 1 over 3 divided by b to the power of 3 over 2. We now use subtraction with the exponents to get b to the power of negative 1 over 3 minus 3 over 2. Therefore, b to the power of minus 11 over 6, or 1 over b to the power of 11 over 6, is the final answer. If you understand everything up to this point, then that's fantastic. Otherwise, it's normal to not get it yet. Take your time, go through the examples, and see how math rules repeat no matter how scary an expression looks. Now, consider this. So far, we have looked at converting a radical to an exponential fraction from the point of having a single variable as the subject. But what if the subject is a product or quotient? How do we apply the conversion? What happens with the exponent? Here's the good news. You just treat a product or quotient subject similar to a single variable. So if you have the square root of xy, just open up brackets and place the xy product inside of it. Then place the fractional exponent 1 over 2 on the outside. Now, instead of multiplying the outside exponent with one exponent on the inside, you instead are going to multiply it with two exponents. So basically, you share or distribute the 1 over 2 exponent with both 1 exponents from x and y. That means we have x to the power of 1 times 1 over 2 multiplied by y to the power of 1 times 1 over 2. And that results in an answer of x to the power of 1 over 2 times y to the power of 1 over 2. Same thing applies to the quotient x over y. Place it in brackets, give it its own fractional exponent, and then share that fractional exponent by multiplying it with the exponent of x and y. That then gives us x to the power of 1 over 2 divided by y to the power of 1 over 2. If you notice, this shows you how a product or quotient under one radical sign can result in each variable having their own radical sign. Now, some of you might be wondering, what happens if the subject is two values being added or subtracted? Then what? Let's say we have the square root of x plus y or the square root of x minus y. The square root of x plus or minus y can be written as x plus or minus y to the power of 1 over 2. But that's it. Nothing more can be done. Let's see why. Based on the sum difference rule, the square root of x plus or minus y is not equal to the square root of x plus or minus the square root of y. The x and y value do not get their own radical symbol. Therefore, the same conclusion must be made with its fractional exponent. X plus or minus y to the power of 1 over 2 is not equal to x to the power of 1 over 2 plus or minus y to the power of 1 over 2. The 1 over 2 exponent is not to be shared among the x and y separately if they are being added or subtracted. Okay, now that we cleared this up, let's look at these principles and apply it to some examples. Here we have the square root of x to the power of 4 times y to the power of 6. We take the subject x to the 4 times y to the 6 and write it out like this. Put the subject in brackets and give it a fractional exponent of 1 over 2. Since x to the 4 and y to the 6 are a product, each exponent can be multiplied by 1 over 2. As a result, we get an answer of x squared times y cubed. With this example here, our subject is now a quotient. We write it out like this by placing a to the power of 6 over b to the power of 3 in brackets and giving it its fractional exponent 1 over 3. Now distribute the 1 over 3 exponent by multiplying it with the other exponents from a and b. This results in a final answer of a squared over b. Now let's check this out. How do we tackle this expression? So the first step is to focus on what's happening in the brackets. Let's turn that radical into a fractional exponent by placing mn squared in its own brackets and giving it its exponent 1 over 3. Now multiply the 1 over 3 among the m to the power of 1 and n to the power of 2. That gives us m to the power of 1 over 3 times n to the power of 2 over 3, all to the power of 4. FYI, if you distributed the 4 exponent by multiplying it by the 1 over 3 first, that would have been just fine too. So we now distribute the 4 exponent by multiplying it with the exponent 1 over 3 and 2 over 3. We now get an answer of m to the power of 4 over 3 times n to the power of 8 over 3. Now I know with this example, it looks like there's a lot going on here. But hey, it's nothing that we can't easily simplify. First, let's convert the radical to an exponent. We place the entire subject in brackets, and then we place the fractional exponent on the outside. Since the index is 5, the denominator is also 5. Now we share the 1 over 5 with both x and y variables by multiplying the exponents. That means x is to the power of 5 times 1 over 5, and y is to the power of negative 5 times 1 over 5. The result is x to the power of 1, or just x, times y to the power of negative 1. Now we can write out the entire expression like this. That's x times y to the power of negative 1 times x to the power of negative 2 over 3. Here we have two x bases that we can multiply together. When we do that, we add the exponents 1 and negative 2 over 3. Now we can combine the x and y variables to get a final answer of x to the power of 1 over 3 times y to the power of negative 1. You also have the option of writing the answer out like this by flipping y to the power of minus 1. That would give you x to the power of 1 over 3 over y. Here's a next expression that looks like too much is going on. it combines multiplying and dividing variables. So first, let's put this product quotient subject into brackets. Since the index is 6, the fractional exponent on the outside will be 1/6. Now we distribute the 1/6 by multiplying it with the other exponents. Lastly, we can take both b variables and divide them. This is done by subtracting the fraction -1/2 from 3/2. So that means b ends up having an exponent of 2. Since a and b are different bases, we cannot add or subtract the exponents. Therefore, when we bring the variables together, we get a final answer of a to the power of -1/2 times b squared. And if you've chosen to flip the a variable, you can get an answer of b squared over a to the power of 1/2. And I think we can end it all here. In conclusion, remember that all radicals can be turned into a fractional exponent. The numerator of the radical exponent is always 1, while the denominator is the index. When you multiply the subject exponent and the fractional exponent, you get the final exponent. If the subject is a product or quotient, then the fractional exponent is shared with each variable exponent by multiplying with them. Lastly, when presented with combined radical expressions with different indexes, consider converting each expression to a fractional exponent, and then using the laws of exponents where necessary to simplify. Well, that's a wrap.